Why don't we go ahead and get rolling? Got a good crew out on the WebEx. Do you want to just go to the housekeeping slide and we'll talk through all that? Awesome. All right. So a few housekeeping items, and then I have the pleasure of introducing those two good-looking gentlemen on the right there. So everyone out there is muted. So if you guys have questions, please just raise your hand in the WebEx, or feel free to chat up some of the panelists, and I'll be there to butt in with that. And by the way, we obviously welcome questions for this. We will have time at the end for questions, but if you have something along the way, feel free to hit that into the chat section, and I'll make sure we get to that as well. When this session is done, we will have a survey that goes out. Just obviously, we welcome the feedback. Want to make sure that these are valuable to you guys, and ideas you have for future ones that might be good as well. So we are going to raffle off whoever fills out the survey a $150 Amazon gift card. So another extra reason. So one last piece of housekeeping. So this session is recorded. So take that for what it's worth. But let me introduce Troy and Joe. So Troy is our resident Wi-Fi wizard. I'm not really certain, what all the numbers and acronyms mean there. Hopefully, it's not your license plate number, but I know it's your radio. But anyway, we'll get into that. Troy and I worked together at Cisco back in the day. Has a super long history in network and wireless specifically, both in the healthcare field and then at his time at Cisco and now at ANM for several years as well. So looking forward to getting his insights specific around wireless. And then Joe on the right, if Troy was a Wi-Fi wizard, I was trying to figure out what we could call Joe. So one was special system sorcerer, so long background in infrastructure based there in New Mexico. Has worked on all kinds of cool projects from, everything from healthcare and military to even like Sandia Labs. So really cool insights around what's happening from an infrastructure perspective, things like cabling, and how Wi-Fi 6 plays a role in that. You think about where the bottleneck moves and how you can be prepared. So, I think it's a cool conversation. One of the things we're happy to be able to provide customers is this transition to Wi-Fi 6 affects more than just radio frequency, right? So being able to tell the whole story and help you guys plan ahead is what we're all about. So both these gentlemen are going to share some insights with you. As I mentioned, if you have questions, pop them in the chat, and we'll make sure we get to them. So thanks again, guys. I will pass it off to Troy, and let's get started.
Awesome. Like Kurt mentioned, my name is Troy Baietto. That's my ham radio call sign, and the repeater here in Phoenix off Mingus Mountain 694 that I hang out in the most. And I've been doing ham radio since I was 9 years old, and there used to be a lot more people on it. Now it's just a bunch of old people talking about ham radio like me. Now that everybody's carrying around cell phones, obviously the popularity has dwindled a little bit, but it's starting to pick up some steam as well in the hobby community and the disaster preparedness community and stuff like that. So, like Kurt mentioned, we're going to talk about Wi-Fi today, Wi-Fi 6 specifically. I'll talk a little bit about the fundamentals of Wi-Fi, go over some of the rudimentary stuff, and then talk about Wi-Fi 6 specifically. We are going to have a little bit of a discussion about 6E, which is the new unlicensed spectrum that the FCC released for commercial use and for home use as well. And then Joe's going to wrap us up with, like Kurt mentioned, the special systems. We're going to talk about how we can make it all work and how we can build that infrastructure to support it, right? So, like Kurt mentioned, any questions on the way, raise your hand, put it in the Q&A. We're happy to field them. And if I don't know it, Kurt will. So we're good to go. So first, what is RF? What is radio besides Bill Gates sponsored mind control, according to my father-in-law? So let's talk about energy, right? So batteries, on your laptop, in your Tesla, direct current. Your typical home is alternating current. And then radio is when we alternate that current so fast it leaves the wire. And so you have that's the birth of radio. I've listed some popular radio frequencies: AM, FM, your TVs, and you got your Wi-Fi there as well. There is a debate at my house as to whether or not that guy. So we measured those cycles per second in hertz. That's Hz. And so there's a debate in my house as to whether or not that the gentleman in the car in front of me was an electrician, or if he was just a senior citizen who wakes up in pain all the time. So the debate is still raging. I wasn't able to actually roll down my window and ask him. But the online community seems to think he's just an electrician, and that's what he is. But he did look like an older gentleman, so I'm assuming it's a little bit of both. So RF and Wi-Fi. Let's talk about how the Wi-Fi and specific to radio frequencies. So again, how fast the current cycles is how radio waves are measured, and in Wi-Fi it's measured kilohertz, megahertz, and gigahertz. Now, a single radio can only transmit one wavelength, so it's half duplex. If you've ever used a ham radio or even a CB or something like that, you know you can't transmit while someone else is transmitting. And Wi-Fi is the same way, and that's why we have to do all of these fancy things in order to make sure that that we can get the density that we need for a half duplex. There's really no way around it, so that's why we're going to talk about some of the features and innovations that folks have done in the Wi-Fi Alliance and the IEEE in order to get around that. Now, the lower the frequency, the longer the wave. And so you can kind of see the graphic there. Higher frequencies have shorter waves, so they actually require more to push them far. And this is why when you're doing site surveys and things like that, and if you've done wireless in the past, you know 2.4 gigahertz, it's a very, very dirty spectrum, but it goes farther physically than 5 gigahertz, which is why obviously ANM, we recommend when you do site surveys, when you're planning your access point distribution and density, you always do it for 5 gigahertz because that's the shortest one. And if you ever forget which one is which, think about actually waving, right? So if you're at a concert or you're on a cruise line leaving the dock, right, it doesn't take a lot of energy to do a large wave. But if you're like a kid and you see your favorite Power Ranger and you're doing a really fast wave, right, it takes a lot more energy. So that's a good way to remember it. So the spectrum is very big. The FCC controls it, and obviously if they can control it, they're going to charge for it, which is why you see the radio spectrum that you see here. 2.4 gigahertz and 5 gigahertz are circled there. We also have the new 6E we'll talk about a little bit as well. So let's talk about Wi-Fi 6 or 802.11ax. Why are we talking about it? Why is it awesome? There's a few reasons, right? The first one, everyone talks about the higher data rates, and that's very important. And of course, we want to go faster. Every few years we have this, that law that states that everything's going to be faster and smaller and all that good stuff. And I think a lot of people focus on the higher data rates, and that's good. We've got new technologies like 1024 QAM, 8x8 spatial streams, and that's going to enable some of the things that we're talking about with augmented reality, virtual reality, these 8K video feeds that we're seeing that are going to start demanding Wi-Fi coverage as well. To me, the next sort of column where you see the increase in overall network capacity, that's where I believe the biggest thing in Wi-Fi 6 are. There's some technologies that we're going to talk about today that, yes, we're going to get faster speeds, but we're also going to get greater density. We're going to be able to service more clients, and we're going to be able to do that as the trends continue to push Wi-Fi to more and more clients. We are seeing greater reduced latency and greater reliability, right? Because of some of these deterministic technologies are allowing us to get wire-like and cellular-like latency and QoS and things like that. And so as we deploy more IoT, there's a lot of municipalities, a lot of manufacturing, healthcare that are deploying a lot of machine-to-machine and edge computing that we're seeing out there. And so all of it requires typically batteries, and so that's where you'll see improved power efficiency, right? The less you use your Wi-Fi, the more your battery works. So if you can get on the air and off the air quick, then you got better batteries. There's also a target wait time, which unfortunately I didn't have time to put in the deck, but for real quick, that is just the wireless device can now handshake with the wireless network and say, I'm going to go to sleep for 3 years in some cases, and I'll wake up and you talk to me in 3 years, right? So these are things like pressure sensors, things like that. They'll say, hey, I'm gonna go to sleep for an hour. I'm gonna wake back up. I'm gonna preserve my battery. So the network is now able to do that. And so one of the things when we talk about capacity is if you think about what's in your home, right? So I have a wireless network at my house. I'm sure many of you do as well. And if you look at your home router, mine happens to be a Meraki router, Wi-Fi access point, and you can see how many wireless devices are in your home. I have 37. I checked this morning, so I've got light switches, I've got a Ring doorbell, I've got a Fire TV stick in it, and everything. And it's becoming more and more. It seems like that technology starts in the home and then translates to the business. And a lot of people make jokes about, oh, they're going to make everything smart now. I've got a smart dishwasher. I've got a smart washer and dryer. I don't actually use those features because they charge monthly and I'm a cheapskate, but we could if we wanted to, right? I could start my dishwasher now. I could check the dishwasher status while I'm at work, right? And that's the kind of things we're talking about. Some people even joke like, one of these days they're going to make smart beds. Guess what they did? So we actually have a customer who is almost doubling their Wi-Fi density overnight because they're purchasing almost 2,000 of these Stryker smart beds for their healthcare system. And again, their big question is, how is this going to affect my network? It's no longer IT bringing these Wi-Fi devices in. It's no longer just people with their laptops and things like that. We're starting to see a lot more departments out there, and it's not even shadow IT. It's they bought the beds. They happen to be Wi-Fi. They want to connect them. How do we do that? And how do we mitigate that? So we're going to talk a little bit about that today. But first, let's get into some of the technologies that makes Wi-Fi 6 so awesome. The first one is quadrature amplitude modulation. So they call them QAM. So you'll hear QAM or QAM, either one, they're interchangeable, but just so you know what the TLA or three-letter acronym is, it's quadrature amplitude modulation. And so basically what we're talking about here is getting density in every radio transmission we do. What is that? There we go. So with one stream, basically, where it's like Morse code, right? So if I wanted to transmit my name, it would be dot, 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 right? So that's TROY in Morse code. That's one stream. That's no modulation. We're not doing any of that. You kind of see we started with 802.11 A, G, and N with 64 QAM. So what that allows us to do is based on the phase and the amplitude, we're able to actually stick a symbol in there of zeros and ones, right? And so with 64 QAM, every symbol has 6 bits in it. With 256, and there's 8 bits, and with 1024, there's 10 bits. So that means that every single radio transmission, instead of just getting a 0 or a 1 in that radio transmission, we can actually put a string of zeros and ones, and depending on the amplitude and phase, we can actually get up to 10 bits now in 1024 QAM. And we'll talk about why that's important in a second. But first, let's talk about channels. A lot of people know that, if you're in Wi-Fi, if you've done this long enough, 2.4 gigahertz only has 3 non-overlapping channels. And again, we don't want the Wi-Fi to be on overlapping channels. We don't want them they don't play nice, there's interference, and it makes your network bad. So for non-overlapping channel, we've got 3 of them in 2.4 gigahertz. We've got more in 5 gigahertz. But we're starting to do something called channel bonding. And channel bonding allows us to take a couple of 20 megahertz wide channels and bond them together and get a 40 megahertz channel, which allows us to get more speed. The problem with that, the downside is the more you bond those channels, the less channels you have, obviously. So that's where when we talk about 6E, that comes in handy. So we can't really bond 2.4 gigahertz channels because you don't want to have overlapping channels. If you have overlapping channels, and again, most people in the enterprise, it's fairly well known, but go ahead and check your wireless network, see if you have anything that's on, any access points on the same channel that are next to each other, that's bad. There's a lot of technology between a lot of vendors that allow them to kind of automatically adjust their channels to make sure that they're not talking too loud on the same channel next to each other. If you have overlapping channels, you are this guy, and that is not a good guy to be, right? You want to stay in your parking spot. You don't want to have those channels overlap. It's not a good thing. Now, if you do start bonding these channels together, you actually start getting higher speeds. And so if we look at an 80 megahertz channel, this is a real world test where we got over 2 gigs per second with bonded channels, right, in 5 gigahertz. And this is the kind of speed we're talking about. We're going to talk about later. Kurt mentioned, we're moving the bottleneck in the network, and so we're going to talk about some of that as well. But this is how we're starting to achieve some of these speeds. Not only are we doing 1024 QAM, we're also putting those channels, we're bonding those channels together so that we can actually get more throughput in one single radio transmission. So when we talk about channel bonding and the QAM, this is just a nerd table here for you. But basically you'll see, and again, this is a single radio, one radio, 1.2 gigabits per second with a single radio with 1024 QAM. at 160 megahertz channels, right? So now if you have a lot of access points out there, you'll see there's like 8x8, 4x4. That's how many radios they have, right? So if you have an 8x8 access point, you got 8 radios. That's over 10 gigs per second, right? So the next technology we're going to talk about is MIMO, right? And so it's sort of a beam steering technology. They used to call it beam steering. The industry term is MIMO, and it started as a proprietary thing that some vendors started doing as, hey, this is something that we do that nobody else does. And then, like most technologies, the IEEE and the Wi-Fi Alliance said, hey, that's a good idea. Let's write that into the standard so that everybody has to do it and the clients have to accept it, right? So this is about being destructive and constructive at the same time. I thought I was going to make a government joke here, but then my wife was like, well, they're never really constructive anyways. But so I said, like my kids playing Legos, right? Constructing, destructing, right? Throwing the airplanes into the wall. So let's talk about some interference, right? So honestly, we're just going to talk about a single radio. On a single radio, if you take one signal and you take that wavelength and you double it, right? So you put the same wavelength on top of it, it is constructive interference. It makes it stronger. If you take that wavelength and put the inverse of the wavelength over it, it's destructive. It's the same thing if you have AirPods Pros, if you have active noise cancellation. So passive noise cancellation headphones, it's just putting cotton in your ears. Active noise cancellation, it's listening to the ambient noise around you, and it's pumping the inverse of that into the headphones. So you're only hearing what's coming out of the headphones, and all of the other noise around you is canceled out. It's the same thing as destructive radio frequencies. It is creating that interference to destroy that, right? So you'll see truckers actually use this. They'll put 2 antennas on their truck, and that way they get constructive interference. They get a stronger signal forward and backwards on the radio, and that's called single user MO or SUMO. So another way to visualize this is this sort of, when you have 2 sources and where they overlap, those points are the constructive interference, right? So now that we've got that out of the way, let's put a radio on each antenna, right? So instead of just one radio, 2 antennas, let's put a radio on each antenna and see all the cool stuff we can do. So multi-user MIMO, here's a good visualization of it. Basically what we're doing is, for the blue user, user 1, we're going to do constructive interference for the blue data, right? And that's why you see that line kind of go into that blue. And the same thing for the red and the yellow as well. What's harder to notice, but I'm going to point it out, is we're also going to be running destructive interference for user 1 for the other 2 data streams. So that way user 1 hears much, much less of user 2 and 3's traffic, right? And so with Wi-Fi 5, it added the ability for clients to actually participate in this and say, here's how you should beamform to me, right? So that was part of the Wi-Fi 5 standard. The clients are now actually active participants in beamforming. Instead of just the access point trying to figure it out, the clients will actually come back and say, hey, you're doing a good job beamforming, or you're not, steer it this way. And so that was Wi-Fi 5. What Wi-Fi 6 allows us, and again, when you talk about spatial streams, this is what they're talking about. Obviously, the more the better, because the more radios we put into an access point, the more we can construct and destruct interference based on that. Wi-Fi 6 added some enhancements, right? We're able to put 8 people in a group now, up from 4. And we're also using some of the other technologies that we're going to talk about in a second in order to do the acknowledgements back, right? So because the efficiency of Wi-Fi 6 is so great, all of the overhead of doing this becomes greater as well. So remember, radio's half duplex. We can only transmit at one time. So yes, the clients are participating in MIMO and sending information on how to beam steer, but they're doing it in a much more efficient way, so that it's not overlapping any of the data that you want to get through there, right? Because it's just overhead at the end of the day. So let's talk about OFDMA, because I mentioned that when we talked about the Wi-Fi 6 enhancements. Because those acknowledgements are using OFDMA, we're getting that efficiency. So OFDMA is orthogonal frequency division multiple access, right? So the MA is important because it's different from Wi-Fi 5. Wi-Fi 5 had OFDM, which is orthogonal frequency division multiplexing, and OFDMA is multiple access. So a lot of people think of it, and it's a little bit of an invalid analogy, but it works just to kind of think of it as like a switch versus a hub. One of the problems with Wi-Fi is, and again, this is like those Wi-Fi beds. There's not a ton of data, right? If you look and do a packet capture on your Wi-Fi, you'll notice that almost 90% of your frames are less than 320 bytes of data. So we're not driving a lot of efficiency because we're not shoving a whole bunch of data into a single frame like we could, right? Think of jumbo frames, things like that. We're not doing that with wireless. Wireless naturally has low amounts of data per frame. And that's things like voice and things like that. When those beds, for example, they're tracking things like, hey, is the bed rail down? Is the brake on? Did the person fall out of bed, right? And those are just quick messages to the server. It's not a ton of data, right? And so there's efficiency problems in that because, again, it's a shared medium. It's half duplex. If we're spending all of our airtime just getting these tiny frames out, we're not doing a very good job of it. So what we do with OFDM is we take that 20 megahertz channels and we do what's called a subcarrier. And so we take 312 kilohertz out of that 20 megahertz and we create these subchannels in it. OFDMA goes a little bit further because we can create more subchannels within a 28 megahertz channel and allows us to do more subcarriers, but it does something else as well. And let's talk about that. OFDM, this is Wi-Fi, right? Everybody gets a subcarrier. Think about it as, the Amazon trucks, right? But think about it this way. Instead of sending one Amazon truck out to a user, I'm sending 8 at one time. But the problem with OFDM is I'm sending one truck with one package, right? So all of that gray space in each subcarrier is empty. So I've got an Amazon truck with one package on it, right? Sure, I'm sending 8 at a time, but it's again, it's not very efficient. It's more efficient than it was before. So basically what happens is you have to wait that entire, it's going to get those 8 trucks. Those 8 trucks come back, get one more package, and then come back out, right? With OFDMA, it's much more efficient because we're actually putting more than one package on each truck. Now we're having 8 trucks leave at the same time. They've got multiple packages. It's kind of like carpooling, right? It's just more efficient. The analogy is that FedEx truck where you see multiple trailers on that truck. Also, if you look at the picture, ANM does recommend that you please wear seatbelts when you're driving. Nobody in that car is wearing a seatbelt. Not very safe. So that's OFDMA in a nutshell. Let's talk about Wi-Fi 6E. So what's so sexy about 6E? Let's say. Anyways, so again, we'll talk about the spectrum. 2.4 gigahertz is right there. You can see 5 gigahertz kind of called out as well. Now there's a new unlicensed spectrum called Wi-Fi 6E, and we'll talk a little bit about that as well. As an Android user, I really like this slide. So back in mid-2020, that's when the FCC said, hey, we're going to give you guys 6 gigahertz, which, the entire spectrum is 1200 megahertz wide, which is awesome. The Galaxy S21 is the first phone to actually have a Wi-Fi 6E chip in it. The iPhone 13 does not. So just an FYI, I'm not shaming anybody here, and the idea is that Wi-Fi 6E uses this spectrum. One of the questions that comes up very, very, very often is, hey, do I need to go out and do I need to upgrade my access points today to Wi-Fi 6E? Until there's that tipping point of threshold of clients actually supporting 6E, then it's really up to each individual use case to make that decision. Obviously, any Wi-Fi 6E access point will support all of the older clients. It'll still do 5 gigahertz and 2.4 gigahertz, but there's nothing I can do to my laptop, for example, to allow it to use 6E without putting a new chip in it, right? Because it's a new spectrum. If my radio and my laptop doesn't support it, it's not something that a software update will do. It's a physical radio that needs to be in it. So just keep that in mind. One of the things that we talked about earlier was channel bonding. So this is 5 gigahertz, and you can kind of see at this little top box here, we've got 25 channels at 20 megahertz. And we do not want the channels to overlap. We don't want to put access points on the same channel. So if you're doing like a floor plan, you're putting access points out there, and you're looking at 5 gigahertz, if you do 20 megahertz with channels, you get 25 non-overlapping channels. you start bonding those together, and you lose the number of channels. Excuse me. And so, you know, at 40 megahertz, you get 12 channels. At 80 megahertz, you get 6 channels. And again, you start getting into that spot where you are with 2.4 gigahertz, where you start having not enough non-overlapping channels to really make a good floor plan and not get that crosstalk between access points on the same channel, because first you got to worry about the access points on a single floor, and then you've got access points above and below you in some cases as well. The new 6 gigahertz bands, there's 59 20 megahertz channels, which is awesome, especially for nerds like me. So you're able to actually start bonding these together, and now you're starting to get 40 megahertz channels. You get 29 of them. So there's still more 40 megahertz channels in the 6 gigahertz band than there was 20 megahertz in the 5 gigahertz band. And now you're starting to see, you know, 14 80 megahertz channels, and now we're starting to see something like bonding up to 160 megahertz channels. You still get 7 of them, which is pretty good. And again, at 160 megahertz, that's where you start getting those crazy speeds and throughput of the Wi-Fi 6 enabled access points. I did put Europe in here as well in case anybody has some international locations, and they're worried about that as well, because while the United States and FCC did release that 6 gigahertz band, the Wi-Fi Alliance and the IEEE also, you know, worked with other regions as well. So it's a little different. Obviously, that's why, you know, when you buy an access point, you got to buy it per region. But you know, just an FYI. Now, some nerd stuff about channel bonding between 5 gigahertz and 6 gigahertz. When access points and when IEEE adopted 5 gigahertz for Wi-Fi, they didn't think about channel bonding at first, right? So it was something that it was an innovation that a lot of vendors did. Says, hey, we can just take some of these channels, bond them together, and get some more bandwidth. The problem is the way that the FCC and government bodies regulate the power in Wi-Fi and radio frequencies. There's a lot of standards and a lot of compliance issues with Wi-Fi because of, you know, if you look at any Wi-Fi card, if you turn it over, there's in fine print it says this device complies with FCC standards. It will not send interference. It will accept all interference, right? And that's something that is universal. With 5 gigahertz, when you bond channels, you lose 3 decibels of signal to noise ratio, which is equivalent to the same to 3 dB decrease in performance. It's the same as putting a wall between you and your access point. That's how much degradation you get in signal strength if you bond channels in 5 gigahertz, right? And so while you get more bandwidth, your range actually gets lower in the 5 gigahertz band when you start bonding channels together. The way that the FCC did the power rules in 6 gigahertz is they measure it differently, first of all, and they also allow it to actually, when you bond the channels, the power efficiency actually increases. So the net of this is with 5 gigahertz, you bond channels, there's a penalty. With 6 gigahertz, it actually favors wider channels. You actually get more power out of wider channels than you do with 5 gigahertz. So what does this mean when we talk about 5 gigahertz versus 6 gigahertz and channel bandwidth and channel width? Not bandwidth, sorry, width. This is sort of a, 80 is the new 20, right? So as people look at, hey, I've got a low, typical, or high density deployment of my Wi-Fi, and we're talking about, typical density is 1,200 square foot per access point, things like that. So this is actually a real world test from a vendor where they actually went out and did a high, typical, and low density, and they looked at how much interference was there, right? Because of that channel density. With 5 gigahertz, because you don't have as many channels, you can't bond those channels together. So as you can see, even with low density, you can't get to 160 megahertz. In the parentheses there is how many channels you get. You only get 2 channels. So it's pretty much a no-go for 160 megahertz wide channels in 5 gigahertz. It's red all the way down. Even 80 megahertz with low density is yellow, right? So you're really only able to get a good floor plan with 40 megahertz channels, and typically that's only in low density, right? Obviously, you can see a lot more green in the 6 gigahertz. You've got 7 channels of 160 megahertz, so you can still do a typical density. It's not red, it's yellow. It's kind of pushing it a little bit, but man, 80 megahertz wide channels, you're still in the green for a typical density deployment, and that is great because you get all that cool throughput and bandwidth, and still you're not running a lot of interference. You don't get a lot of noise. That noise floor stays low. Kurt, do we have any questions so far?
Just about the recording. This will be recorded. I know there's a lot of content. We'll make the recording available to you guys. But I do think this might be a good time to pause and see if anyone does have questions. Please raise your hand or hit up the chat, and we'll make those known. But I think right now that clears it. We'll give people a second in case they do have some questions. Give you a chance to pour that water. Sure.
Awesome.
A lot of good content, a lot changing constantly.
Yeah, and again, it's all driven by the consumption of Wi-Fi, right? And it's funny because I've had customers say, like, we're going to open a new facility. It's going to be Wi-Fi only, right? And we've seen some success with that. I mean, eventually they come back and they're like, oh, wait, we need a fax machine, so I guess we do need some cables. So not a lot of Wi-Fi fax machines out there right now. But everything else, like I said, it's a lot of people are demanding that Wi-Fi be available. I know that when I go to hotels and they're like, there's actually a resort not too far from me up by Lake Pleasant here in Arizona, that one of their claims to fame was that they didn't have Wi-Fi because you're supposed to disconnect. And that lasted about 6 months after they opened, and then they were like, okay, we've got to put Wi-Fi in because everyone's demanding it. That was a fun little marketing term. But
yeah, so we got a few questions here, so let me pepper you, and we'll see how we do. One here from Patrick: is 6E available on Meraki APs now, or will it be coming shortly?
So channel bonding in Meraki is available now, I believe. I can make sure, but obviously there's certain access points will support it and some won't. I don't know if it's in the dashboard yet, but I think it's in beta, so I'll check.
Okay, so 6E available. We'll confirm.
Oh wait, okay. 60 meg? Did you say 60 megahertz?
He said 6E available 6E. On Meraki.
No, I'm sorry. I thought he was talking about channel bonding in Meraki. So I don't believe that Meraki right now has a 6E access point available. I'm sure that they've got it under the cover somewhere. I know that Cisco and HPE Aruba both have. They've very recently come out with 6E access points. I don't think Meraki has yet.
Okay, we'll confirm. But yeah, good question. Another question here, curious about cabling infrastructure needs and switching needs for 802.11ax APs. I think we're going to get into some of that with Joe here shortly, but maybe if we don't answer that in Joe's session on cabling and special systems, we'll circle back on that one. And then Dane asked, what are the typical environment interference for 6 gigahertz? Example, 2.4 has Bluetooth and cordless phones.
Yeah, that's a good question. So there's a couple with 6 gigahertz, right? So 2.4 gigahertz is very, very dirty. It's Bluetooth, it's microwaves, it's baby monitors, and cordless phones. If people remember you remember when the cordless phones were like, we're 900 megahertz cordless phone, and then became 2.4 gigahertz. So it's 2.4 gigahertz is very, very messy. 5 gigahertz, it's much more clean. With 6 gigahertz, the nice thing about 6 gigahertz is the only thing that's in that range is airport radar. So the only thing that's really going to interfere with 6 gigahertz is if you're near an airport. But even then, when you go back and look at the 6 gigahertz band, you'll see this band right here in the middle. Oops, let's go over here. Let's move my mouse. So between 6425 and 6525, that's grayed out because that is not available because that's for other things. That's where the interference happens, so that's why they grayed it out. So it really shouldn't get you inside the unlicensed range. But it's just as clean as 5 gigahertz, so you won't find many devices in your environment that's going to affect 6 gigahertz clients. Good question, though.
Cool.
All right.
I think that's questions right now. So obviously, Joe, there was a question around cabling needs and switching. We may have to circle back on the switching with Troy here, but that was a nice segue.
Well, I'm not done yet.
Oh, you're not?
No.
Oh, you're right. Cabling dots, you're going to jump in. We'll get there. Yeah. Jump in the gun.
So one of the things that I wanted to mention before Joe takes the helm is mgig. So multi-gigabit, when we talk about switching infrastructure, Kurt was right on the nose when he said that, hey, the bottleneck is moving, right? And so we've got access points that now can service clients over 1 gigabit up to 10 gigabits in but that's in a perfect environment, and that's just on paper, right? But still, we're seeing real world tests where we're getting 2 to 5 gigabits per second in Wi-Fi 6 and Wi-Fi 6E with those bonded channels and things like that. So most access points are plugged into the same switches that your printers and your phones are. They're 1 gigabits per second, right? Some vendors, and again, this is people like Cisco, Aruba, Mist, and some of those other ones out there, they're actually putting more than one uplink on an access point, so that way you can kind of bond those cables together, so you can kind of double the speed there. But multi-gigabit, or you'll see mgig, is a standard that allows over 1 gig up to 10 gig capacity on yours, a standard Cat6A cable. You can kind of see the table there of what we're talking about as far as speeds you can expect based on the cabling plant that you have today. What we've seen a lot of customers do in environments with high density where they start deploying Wi-Fi 6 and Wi-Fi 6E is maybe I have a stack of switches, right? Or I have a modular access switch, and so usually what we'll see is, hey, add an mgig switch to the stack, add an mgig module to the chassis, and then plug in your high density, where you have access points in high density environments, plug those into those mgig switches, and those access points, if they support mgig, will now operate up to 5 and in some cases 10 gigs per second. Now, does it actually work? Yes, it actually works. So on the left is a Wi-Fi 6 access point plugged into an mgig switch, and on the right is a gigabit switch. You can see the throughput obviously is almost double that of a regular gigabit switch. So we're actually getting 38% more datagrams, which is a lot of datagrams. So definitely seeing a lot more throughput on an mgig switch. And again, this is just making sure that this is really the first time that we've seen the wireless standards actually faster than the wired backhaul that they're plugged into. And so it's creating a lot of unique challenges. So Joe's going to solve them all.
Well, at least that's the goal, right? Hello, everybody. I hope you're having a wonderful day. Thank you, Troy, for the great presentation.
Hey, Joe, before you jump in, we got a question specific to mgig, so why don't we take that? So Dan had a question. When you have low channel bandwidth, is there any advantage to mgig?
So if you have low channel bandwidth, is there any advantage to mgig? Not really, right? So if you're not getting, but that being said, if you have a high density, obviously that could help. The other thing is we're seeing more than just access points having mgig capable ports. The newest Mac Pros actually have mgig ports on them as well, so they'll support mgig. We're seeing security cameras, so IP cameras are actually starting to support mgig as well, so you get those high fidelity 8K video on surveillance and things like that. So we're seeing more and more devices actually support mgig, not just access points. So yeah, obviously if the bottleneck is, if your access point can't push more than 1 gig because of its radio standards, then you're not going to get a lot of advantage out of it. But obviously, it's something that if you're planning on a refresh, things like that, the price of an mgig port is very, very, very close to the price of a standard gigabit port. So most of the time, it's just one of those things where if you're deploying high density wireless or high speed wireless, add a switch to the stack, things like that. If you're doing a refresh, that's when you would keep it in mind and look at, hey, where do I sprinkle in some mgig where I need it?
All right. Thank you, Troy. As Kurt and Troy mentioned, I'm going to be...
Sorry, guys. We keep getting questions, which is good. When would you see the advantage then, Troy? So 40 or 80 megahertz?
Yeah, so 40 megahertz. So if you look back on a slide a while ago, we were able to get almost over 2 gigs of data at 40 megahertz, and that is a real-world test. Oops. So this is at... this is at 80 megahertz. So at 40 megahertz, you're still getting over a gig, right? You're getting, I think, 1.2 gigs per second. And again, that's for one client. So the more clients you have, the more density you have, the more throughput it's going to require. So yeah, even at 40 megahertz, the second you start bonding, I would start looking at mgig. And the cool thing about MGig, if you're just adding an MGig switch to a stack or adding an MGig module to a chassis, the cool thing is if you want to pull out a switch from that stack and replace it with an MGig switch, you can probably repurpose that switch somewhere else for a new building or something like that. So we're certainly not asking you to throw away your non-MGig switches, just kind of augment them with MGig technology.
All right.
Oops.
Okay.
Cool.
Far.
For real this time, Joe.
All right. No more questions. Okay. So
No,
Kurt,
if we got more, we'll take them at the end too. But go ahead, Joe.
okay. I hope everybody's having a great day. As Kurt and Troy mentioned, I'm going to be discussing the cable infrastructure, what's needed for Wi-Fi 6 and even other technologies that will come after Wi-Fi 6, such as 7. I'll also touch on a newer technology that's gaining some traction in certain markets, which is PON. So let me start off by discussing Bixie. A lot of you might be familiar with Bixie. It's a professional association supporting the advancement of the information and communications technology profession. Bixie is the preeminent resource for the connected world. Their headquarters is in Tampa, Florida, which I've been, by the way. I took a course out there about 15 years ago. Awesome facility. Bixie membership spans nearly 100 countries. The TDMM is the flagship manual for Bixie, and it is the leading reference document for all ICT professionals designing digital infrastructure projects. Bixie recommends Cat 6 as the minimum performance level for horizontal balanced twisted pair cabling.
Yeah, and one of the things I think the other thing when we talk about MGig and whether or not, you know, when do I deploy it? If you're running a lot of Cat 5, then you're only going to get, you know, up to 2.5 gigs on MGig. So keep that in mind as well.
Sure. And as I mentioned, Bixie recommends Cat 6. However, manufacturers and we as a special systems integrator recommend installing 2 Cat 6A cables for horizontal balanced twisted pair cabling links. Category 6A cables are the fastest growing cable segment on the market and are recommended for wireless deployments because they are required for 10G base T and have optimal PoE performance. Category 6A allows you to accomplish 10 GPS and speed up to 328 feet. Please note that Category 6 cable will also allow for 10 gig speeds. However, the distance limitation can vary depending on the crosstalk factors, anywhere between the range of 110 to 165 feet. So as you can see with 6A, you know, you can get out to those farther devices and still get that 10 gig speed. Siemens and many other manufacturers' recommendation is that 2 Category 6A or higher performing cable drops, such as fiber, be available at every wireless access point. Manufacturers also recommend utilizing shielded 6A cable. Reason being is the non-shielded cable tends to heat up high, you know, a lot greater or faster than shielded cable does. And if you have large cable bundles, that may bleed over to the other cables in the bundles, which in turn will affect the signal transmission. So now, obviously, there's pros and cons of using shielded versus non-shielded. Shielded cable is a little bit more expensive, but again, you know, it's definitely recommended for high PoE applications. Now, the reason that we're recommending two cable drops to your access point, there's a couple of different reasons, but it will ensure that your facility is future-proof for expansion to Wi-Fi 7 and other succeeding technologies. It also allows for backup power capabilities in the event that there is a failure on a power source. Deploying 2 Category 6A shielded cables will also support link aggregation of not only today's requirement, but future proofing to 3.5 gigabits per second and higher. And as you can see from this chart below, it talks about 802.11, where Cat 6 was recommended. And then once you got into 802.11ac is when you started seeing the recommendation for Cat 6A. And with 802.11ax, which is Wi-Fi 6 being implemented, you're still seeing 6A. And then once you see the recommendation over here in the Wi-Fi 7 column, that's where you're seeing the recommendation for 2 Cat 6A cables. So if you're going to be redoing your cable infrastructure, one, it's not that much additional cost to deploy two cables versus one. You're essentially pulling a drop to the location already, so it's a little bit of additional material costs, a little bit of extra labor, and it'll future-proof you for the Wi-Fi 7.
Yeah, I think, Joe, you bring up a good point about PoE, and that's something that I didn't mention. But if you can't supply, when we talk about Wi-Fi 6 radios, and I mentioned like there's 8 radios, per spectrum, right? You have to power those radios. If you don't supply the correct type of PoE, it'll start shutting those radios down, and all of those features that we're talking about as far as spatial streams and stuff like that gets diminished, and your bandwidth actually gets reduced because the access point will actually start powering down some of its radios in order to operate at some of those lower PoE rates. So I'm glad you brought it up, Joe.
No problem.
Just a quick clarifying question. We had a couple of questions around when you talk about two Cat6a cables bonded. Are you talking about port channel or something else? And obviously, the implication there is if you're running two cables, running them together, is there obviously a hit on the number of ports on your switch that you're using as well?
So each cable would require its own switch port.
Yeah.
Yeah, and as far as link aggregation, again, that's if you have an access point that supports it as well. So we're seeing access points out there with two 1 gig links, and you can aggregate those. Obviously, you would need two switch ports to plug them into. We're also seeing 2 M gig as well, so you can start aggregating those. But we're also seeing what a lot of customers are doing as well is running two cables just in case one of them fails as well. So sometimes they're not using both cables, but hey, if we've got somebody on a ladder, popping up ceiling tiles and things like that, running a cable, running an extra cable per access point doesn't hurt, right? And if you're already running a cable, the cost isn't like running a brand new cable, right? There's a little bit of a material cost, but the labor is mostly the same because you're already running a cable there anyway. So a lot of facilities are still running two cables just for backup. And in that case, it's kind of a warm or a cold spare where you wouldn't need the switch port, obviously, if you're just using that in case something gets cut or that wire goes bad.
Yeah, and that's a good point as well, because a lot of times when there's work being done in a facility, other contractors that are in the ceiling space, it's not uncommon to have a cable damage during the installation of mechanical ducts or heavy pipes. So having that second cable as a spare will certainly be beneficial. Here I put together a little chart. Just gives you a little cost comparison, just kind of touching on what I mentioned about the cost of installing two cables versus one. Now, obviously, as material and labor costs escalate, they continue to escalate. This chart's going to continue to increase. This is just for your typical installation, what we're seeing on a normal condition project, and it gives you an idea, and it kind of emphasizes the point that both Troy and myself mentioned about the cost.
Yep.
Here's the IEEE 802.11 standard. You can see when the different standards were released. The 802.11ax standard was released in 2019 using the 2.4 gigahertz and 5 gigahertz frequency, and your maximum data rate is 10 to 12 gigabits per second. Future-proofing networks is recommended by the ANM structured cabling team of two Cat6a cables per wireless access points, as we've already discussed. As the IEEE standards evolve and change, bearing the cost of structured cabling now saves for future investments of new hardware deployments. So, as I mentioned earlier, we are going to talk a little bit, now that we've talked about the infrastructure required for Wi-Fi 6, we're going to get into, touch on a new, I shouldn't say new technology, it's been around for some time, but it's gaining some traction. It's called PON, and if some of you are familiar with PON, the acronym stands for Passive Optical Network. What is PON? As I mentioned, it's Passive Optical Network. PON is an alternative to traditional Ethernet deployments. PON is a system that distributes single-mode fiber optic cabling to optical network terminals at the edge with a point-to-multipoint architecture. There are many different standards of PON, APON, EPON, or GEPON, GPON, 10G, EPON, and RFOG. Voice data Voice, video, data, cameras, access points, access control devices are all capable of connecting to the optical network terminal and utilizing the PON infrastructure. Going to go into the architecture of PON just a little bit here. The system architecture utilizes optical splitters to divide the downstream signal from a single optical line terminal into multiple downstream paths to end users. Excuse me. The splitters also combine the multiple upstream paths from end users back to the OLT. An enterprise PON network consists of an optical line terminal in an MDF or IDF room, commonly referred to as the head-end location. Single mode fiber optic cable is connected from the OLT or the head end to an optical passive splitter. From that passive splitter, passive meaning that it doesn't require power injection, from the splitter, a single or a dual strand fiber optical cable is routed to an ONT, which is installed at the edge. Normally you'll see the ONT installed, above the ceiling. It's common. In some instances, you might see it wall mounted or even desk mounted for an office that has a phone, a computer, and other IoT devices. And then from that ONT to each connecting device, you'll take either Cat6 or 6A cables and then connect them into the system. So typically from the ONT, we're talking about very short runs. Normally you can accomplish these runs by installing patch cables. That's the goal, is to push the fiber out as close to the edge as possible. So you have higher bandwidth pushing out. And then it makes for a much simpler installation when you have to reconfigure a room or a space in a building. So instead of taking your cable all the way back to an IDF room that could be 250 foot plus away from your device location, now you're taking a cable maybe 15 feet, right, by extending a patch cable. Excuse me, guys. Is PON right for you? So some of the advantages of PON, and I've touched on a few here. There's obviously a lot more than this, but one of the main advantages is your speed and bandwidth. In the 90s, it was a goal to try to implement fiber to the desktop to accomplish higher bandwidth, and that caught on somewhat. You saw the deployments mainly for military applications. PON is very similar to fiber to the desktop. It's in that you're taking the single mode fiber all the way out to the edge. Now, another advantage to PON is you can go well above the 328 feet channel length limitation that you have with Ethernet. So, that allows you to connect to cameras that might be 1,000 feet away from your IDF or, other devices. And with moving on to the next point that plays into it is, being that you're able to go to greater distances, now you can reduce the amount of IDF closets that you build out. So if you're building a new facility and you implement a PON system, in some cases you can have one closet that feeds that whole facility, depending on your campus layout. Whereas in most traditional Ethernet deployments, you might have a closet, an IDF closet on each floor, and in some instances you're going to have multiple closets on each floor due to that distance limitation that I mentioned earlier. Now, obviously, when you're reducing your amount of IDF closets, you're reducing the amount of active equipment. So in that instance, the cost is driving down. And then another advantage to deploying a PON system is that fiber is not susceptible to interference like you have with copper cable. So, oftentimes when installers place cable above a ceiling space, if they're not following BICSI standards and the National Electric Code, the distance limitations or requirements from power sources that emit EMI, then you gain what's called interference over your cable. So with fiber, you don't have those issues. So if you have a tight ceiling space and you've got fluorescent lighting and there's really no way to avoid that, well, you're in luck with fiber, because it's not gonna, that interference will not bleed over into that fiber cable. Another pro to a PON deployment is reduced energy consumption. So Imagine the ongoing costs of energy, inefficient equipment, and equipment needed to operate in a traditional Ethernet LAN, and the additional energy cost to cool or heat the closet space. So achieving more than 50% savings by eliminating active switches, UPS, devices, and additional power demand is a year-by-year cost-effective annuity. So, you can start seeing some great savings in energy by having less IDF closets and in turn having less active equipment. So another point is reduced energy consumption. Another huge advantage is the installation savings. Now, I want to clarify this because a PON system is a little bit pricey to deploy unless you're talking about, you know, so I'd say probably approximately 500 devices or more. Um, but what I mean by installation savings is the point I mentioned earlier is, once you deploy a PON system, when your ONT's out at the edge, instead of running your cable, if you've got to add two cables to a room that was reconfigured, um, instead of having to build a pathway and pulling two cables, 250 foot plus feet back to your IDF room, now you're just taking them to the next room over that has that ONT. So it's very similar to a modular deployment where you use Mutoa in that you can easily add devices in without a lot of additional labor. And then one huge advantage to PON is that you're future proofing your facility, right? With fiber, you have unlimited bandwidth, more specifically single mode fiber. So, whereas with 6A or even Cat 8 that's available on the market, you do have um, limitations to bandwidth, right? And so with single mode fiber, you don't have that limitation. And then one other huge factor is the reduced amount of cabling above the ceiling. So if you've got your ceilings are cluttered with air conditioning ducts, large sprinkler pipes, electrical conduits, and you don't have a lot of room above the ceiling to install a cable tray or a J-hook pathway system for your Cat 6 cable infrastructure. You're talking about a single strand fiber is easily half the size or the outside diameter of a Cat 6 cable, and probably even significantly less than a 6A cable. So it's certainly a huge plus there. If you've got a cable tray that's already cluttered full of existing infrastructure in place and you have minimal room, this is another thing to consider is deploying a PON infrastructure. Now, what I did here is I talked about a little bit of some of the disadvantages of Ethernet, physical limitations. You've got distance limitations, which with Ethernet, which I've already mentioned, you have a total of 328 foot with your channel, which is you've got 295 foot on your permanent link, which is from your connecting jack all the way back to your patch panel, and then the remaining footage is allowed for the patch cables on each side. So uh, it's really an issue when you're doing a camera deployment, is when you start to see a lot of issues with that distance limitation. Now, so another disadvantage is point to point connections, whereas with PON you have point to multi-point. Now, I kind of talked about this already, but with Ethernet, there's more active equipment needed in your MDF and in your IDF rooms. And another common thing with an Ethernet deployment is that you'll have your cable infrastructure will have to be replaced as new technologies develop. Now, it's not uncommon to hear every 10 years to upgrade your cable infrastructure. And I think that's pretty spot on now with the way the technology is developing. And I mean, you can certainly try to maximize your infrastructure a little bit longer than that. But with the demands on the network now, it's pretty common to have end users ripping out that old infrastructure every 10, 15 years. In conclusion, as PON technology continues to improve, the strategic and economic advantages of PON deployment become more compelling. PON deployments will eliminate the traditional rip and replace deployment that comes along with category related Ethernet deployments. And then single mode fiber optic cable deployment is the way to ensure that all future bandwidth needs can be met in your facility.
So, yeah, This was really interesting to me, Joe. This was something that I didn't really know much about before we started putting this together. And then, as you guys started talking about it, I really saw some really great use cases for PON. And, I think obviously in Greenfield, when it's like, hey, I've got a new building, it's very easy to start looking at this and saying, hey, is this right? So that way and I've seen some videos from like Corning and some of these other vendors as well. And it's cool to see the cable trays with like one cable in it, and then they distribute that at the edge. The other thing that I saw was a really cool use case, is maybe I've already got all this Ethernet, but I've got one use case like you mentioned where we've actually got a customer that we're talking with that it's a large farm, and they're like, we want to put Wi-Fi and cameras on, to watch these cows, and I thought it was like, you see if the cows were doing anything bad. It turns out it's for, if someone gets hurt, they have video backup and stuff like that. But we were like looking at this, and these troughs where they're doing the cow feeding and milking and stuff are so long. It's actually more than that 328 feet. So we can't do a standard Ethernet cable. So when we started talking about this, I actually was like, hey, that's great. One question I have for you though is, what are the manufacturers that are kind of big in the PON space? I actually looked it up. And Cisco actually makes, so I'm from Cisco, so I was like, I wonder if Cisco's in this market. They are. Their line of PON switches, ironically, are called Catalyst PON. So if you guys want to look that up. But who else is kind of in this space? Who do we work with mostly for it?
So we implement the Corning SD-LAN solution, which is a real state-of-the-art solution. I do have a preference personally, not just because we push the system, but what I like about the Corning SD-LAN is you can utilize your infrastructure for active E or passive PON. And so, of course, you've got the big players like Adtran's in the market. You have combination of Tel Labs with other passive components. So Tel Labs is the active side of things that you see commonly implemented with the CommScope solution. Just about every cable manufacturer has come out with a passive line for PON now. And like I mentioned earlier, the technology has been around for some time. It's just now we're starting to see it gain more traction. I think, when technology is new and people are used to doing it a certain way, it's kind of hard to buy into a new concept. Where we've really seen the PON take off is in hospitality, although it's not limited to hospitality. Troy just gave a perfect example of a scenario where PON would be beneficial to implement. Sandia Labs here in Albuquerque, in fact, had at one point the largest PON infrastructure in the nation. It may still be. So what they deployed out there was a CommScope, CommScope PON solution with Tel Labs electronics.
Cool.
So for the cable manufacturers that aren't in that electronics market, they'll often partner with a Tel Labs or another manufacturer like that.
Awesome. So I think Kurt would be mad if I didn't mention, if you want to learn more, reach out to your ANM account manager, and we'll certainly set you up with somebody on Joe's team and get you some more information.
Yeah,
absolutely.
That's good timing. We've got one other question. If you guys have questions, we're at the end here, so feel free to chime in with them. But appreciate both of you guys walking through that. So the question that's in the queue here now for you, Troy. So the Jerry references that interference has always been the Achilles heel with wireless. Neighbors, same device, microwave, all that sort of thing. So what advances have been made to address the challenges of interference other than just stronger APs?
Yeah. So that's a good question. So there's a couple of things that we've done for interference. The first one is a lot of vendors are now putting spectrum analysis chipsets in their access points. So access point radios typically only operate in that the unlicensed band, the bands. However, I know HPE Aruba does it. Cisco calls it clean air, right? Where they actually put an RF chip, a spectral analysis chip in the access point itself that looks at not just the Wi-Fi bands specifically, but it'll also look at some of the crosstalk bands around it as well. So it'll actually start identifying, hey, this is a microwave, this is a Bluetooth, this is a wireless monitor or something like that. And so having the ability to have that is good, because once the access point identifies that interference, remember I talked about destructive interference, it can actually start trying to null that signal out, and it'll do the best it can to change channels or get around it, things like that. So that spectrum analysis is one thing. The other thing that we're seeing a lot of is we're starting to see more flexible radio. So we're seeing access points coming out with what's called an XOR radio or an XOR radio. And what it allows it to do is it allows it to actually turn off the 2.4 gigahertz and then switch its spectrum to 5 gigahertz. So you'll actually have an access point with two 5 gigahertz radio arrays on them. What's nice about that is you get what's called a macro and a micro cell. And the cool thing about that is, because one of the things that sucks about interference is if your interferer is on the fringe of your Wi-Fi, right, and that's typically where they are, you don't put interfering things right underneath your access point, then they get the macro cell. And so all of those people that are on the fringes of your coverage are slowing everybody down because they're doing retransmits or getting that interference. So with things like flexible radio assignment and being able to do a macro micro cell, if you happen to be pretty close to the access point and you're in the micro cell, then you're on a totally different radio and a low power radio than the folks on the outliers where those interference are being seen. So that's another thing that we're seeing for interferers. I think there was one more that I wanted to talk about. I can't remember what it is off the top of my head, but there's definitely some cool stuff. The spectrum analysis is great. Obviously, one of the things that we recommend at ANM is a site survey, a passive site survey. Go out there and just start listening. What is out here? Audit those things as well and try to find out what they are. A lot of times when we see a lot of interference, especially, I came from sort of a healthcare background, and that there's a ton of not just interference but attenuation. There's Faraday cages in the MRI room. There's the facilities construction. Where are the pipes in the walls? Things like that, right? And so you'd be surprised how many quote unquote shadow ITs that we're seeing out there that are very, very destructive for Wi-Fi, because a lot of times these vendors that are deploying, manufacturing these things aren't listening to Wi-Fi standards. They're just, creating 2.4 gigahertz. The worst that I've seen is a baby monitor, and I've seen this demo where they'll take a baby monitor and they'll turn it on next to a spectrum analysis, and all of a sudden everything goes dark because they didn't build that with Wi-Fi in mind. It's not actually Wi-Fi standards, so they're not adhering to any of those standards, and you've got a lot of interference. So it's good to do a site survey, understand where those interferers are, and try to audit them and tell those people to turn the power down.
Yeah, John mentioned that being in healthcare as well, it's just tons of devices, right? And I know based on your background, Troy, you've seen that, but it's definitely one of the most challenging. You mentioned a cow farm. That sounds interesting, but I think healthcare probably takes a gig.
Yeah, healthcare and manufacturing are really difficult, especially manufacturing. It's interesting because it's attenuation, it's reflection off of all of the metal surfaces, typically clean surfaces. But a lot of people don't think about how tall the ceilings are. If you put an access point 80 feet above you, you're gonna get really bad coverage. So it's really interesting when I walk in and I see an access point way up there, not on a down rod or anything like that. So
Yep. Call out. Well, good feedback. Thank you guys for the questions. It's super helpful. Hopefully that's helpful for you guys. We appreciate you joining this. We will obviously get you guys the wireless thermometers that we talked about as well. So keep an eye out for that. And then also keep an eye out for the post survey. So we really appreciate any feedback you guys have in terms of what we can do to make these events better, what topics are useful, which ones aren't, so we can do events like that in the future as well. So keep an eye out for that. Whoever goes through that will raffle off a nice prize. So thanks again, Troy and Joe, for putting this together. Thanks everyone on the customer side for attending. If you guys have any questions, obviously we're here to help. So thanks again. Have a great day.
Have a good day, everybody. Thank you.
See you guys.